Hi, in this video I want to show you an example of a problem where we have to make our own probability distribution. Okay, and we're going to be using the probability that you've been studying. So let's read this example. It says you roll a die. If it comes up as 6, you win $100. If not, you get to roll again. If you get a 6 the second time, you win $50, but if not, you lose. Okay, so we need to make this probability distribution table, and we're going to have 2 rows. The first thing we need to think of are our different events or outcomes, and we call those X. And then the bottom row usually is the probability. We could call that P of X. In other words, it's the chance of this outcome happening. Okay, so what I like to do is list all the outcomes first and then try to figure out what the probabilities are. So you roll a die. If it comes up 6, you win $100. If not, you get to roll again. If you get a 6 the second time, you win $50. If not, you lose. Okay, and then the other thing we want to make sure we're making the distribution for the right outcome. This one says the amount you win. So we need to be sure to put the winning amount up here. So we could either win $100 or we could win $50 or we could lose, which is no dollars, sadly. Okay, so those are our outcomes. And now we need to find the probability of each one. I wish I had a die here with me. If I had thought about it, I would have grabbed one. You roll a die. If it comes up a 6, you win $100. So what's the chance of getting a 6? If you said 1/6, you're right. And also, if you want to try this, feel free to pause it and do it yourself and then check your answer. Okay, so if we get a 6, we get $100. Seems like pretty good odds to me. If not, we get to roll again. And if we get a 6 the second time, we win $50. Okay, so for this one, we're rolling 2 times. First, we would have to not get a 6 the first time. So what's the chance of that? The chance of not getting a 6. Well, it would be everything except this, right? So 5 out of 6. That means we got a 1, 2, 3, 4, or 5. We didn't get a 6. So there's 5 ways to do that. And then dice rolling is independent because it stays the same every time. It's the exact same probabilities every time. So we can multiply those together because one dice roll does not influence the next one. What's the chance of getting a 6 the second time? Well, it's the same probability, 1 out of 6. So if we multiply those together straight across, it'd be 5 out of 36. Okay, what's the chance of winning nothing? Well, there's a couple ways you could do this one. One way is to say, okay, well, that means we would not have gotten a 6 the first time. So there's 5 out of 6 chance of that. And then we would not get a 6 the second time. We're using complements here. So that is also 5 out of 6. So that would be 25 out of 36. Now, I'm curious if you thought of another way to do this. We could also use the complement. If we know all of these except 1, we can subtract from 1 to find the remaining one, because in order to be a probability distribution, we have to have 100% or 1 probability of 1. So if we did 1 minus 1/6 minus 5/36, we should also get that same answer. Let's try it. I have a nice fraction button on here, so I'm going to use it. 1 minus 1/6 minus 5/36. 25/36. Now you could also use decimals for this. You might run into a little bit of trouble with round off error, but it doesn't really matter to me, fraction or decimal. let's see, we could have done, again, we could have done 1 minus 1 divided by 6 minus 5 divided by 36, and that would give us our decimal answer. But then we would have to round this off. So be careful with my open math. You might want to stick with the fractions. Okay, so that is how to find or how to make a probability distribution if you don't have one to start with. Okay, now finding the expected value and the standard deviation are just like we did in the last video. So I suggest trying it out. Just pause the video, try it, and then start it up again and watch the solution. Okay. Okay, so I'm going to calculate the expected value, and that's going to be the amount times its probability. Okay, so I've got each amount times its probability. The 0 is going to be 0, right? But I'm writing it anyway, just so we have it there. 100 times, and again, you can, we're going to get a decimal at the end, so you could either use a fraction or a decimal way of doing this. I could do 100 times 1/6 plus 50 times, whoops, 5/36 plus 0. Again, I don't really need that number. I know it's going to be 0. And this gives me a really nice fraction, so I'm going to use the decimal key, and I get $23.61. I'm going to be sure to put my units on here, which is dollars in this case. Now, we could have done it, if you prefer, just to do it with the decimals. 100 times 1 divided by 6, or just divided by 6, plus 50 times 5 divided by 36, plus 0 times 25 divided by 36, and we got the same thing, so you could do it either way. Okay, now pause it if you haven't done the standard deviation yet and try it. It's also always a good idea to check your mean first before you start doing this big long calculation. Okay, so our variance is going to be $100 minus $23.61 squared times 1/6 times the probability that that happens, plus 50 minus 23.61 squared times, where am I, 536, plus 0 minus 23.61 squared times 25/36. Now this time I do have to have the 0 term, which is kind of why I do it. I just use it all the time. Because when we're subtracting something from 0, this is not 0 anymore. So we do have to do the 0 term in the variance. Okay, let me put this in my calculator, and I think I'll just do the decimals because it's easier. Let's scoop this up. Okay, I'm going to do one term at a time. 100 minus 23.61 squared times 1 divided by 6, or you could just do divided by 6. Okay, then plus the next term, 50 minus 23.61 squared times 5 divided by 36. Enter. Getting big numbers, right? Because we're squaring these deviations. Plus the third term, 0 minus 23.61 squared times 25 divided by 36. Also, if you rounded your mean to a different place, that's fine. I used 2 decimal places because it's dollars and cents. Okay, 1456, 40. Yep, that's what I got last time too. So 1,456 and 40. But remember, these aren't dollars because we squared everything. So these are square dollars, or dollars squared, which doesn't really mean anything to us. That's why we need to get our standard deviation by taking the square root. One, 4, 5, 6, 40. Square root of that. Now we're in dollars. $38.16. Okay, so now I can put my dollar sign on there. Okay, so what does this mean again? On average, if we played this game over and over and over again, we would expect to win on average $23.61 per game. Okay, not bad, right? It varies quite a bit though, which you can see because it goes from 0 to 50 to 100. So on average, we would vary from that by $38. Okay, although we couldn't go below 0 because we're talking about winnings. So we would just kind of cut that off at 0. Okay, so that's kind of assuming this game is free, right? But probably not going to happen that way. Would you play this game if it costs $25 to play? I'll let you think about it for a minute. You can pause it if you want. If you said no, I'm kind of with you on that. This is saying on average we would win $23.61. So why would we pay $25 to play each time if we're only going to get back on average $23.61? Now we could get lucky and get $100 early on, right? Before we've spent less than 4 times maybe before we spend $100. But in general, you want the expected value to be higher than the amount you're going to pay. So I personally would say no, because we would only win $23.61 on average. On average per game. This is the way most lotteries and casinos work, right? They have a margin where the customer or the player is going to have an expected value less than generally what it costs to play. And that's because they're in a business and they're trying to make money. Okay, so a fair game is defined as a game that costs as much as its expected payout. In other words, the expected profit is 0. So if it would be a game where you would expect to break even on average in the long run, okay? Some people would say, what's the fun in that? It's gambling after all, right? And you don't see this many fair games, but that's what it would be. So if this game costs $25 to play, sorry, I said that wrong. If this game costs $23.61 to play, if we paid that much each time, and on average we expect to win that same amount, then in the long run we would break even. So the price, the expected value, if they charge that much, would make it a fair game. Okay, do you think lottery and gambling games are usually fair? I was kind of talking about that a second ago. And usually not. Usually they are putting they have administrative costs or business costs, overhead, and then sometimes profit. Now, I believe the lottery is non-profit, but other things that are profit also is going to come out of that, the money that you're paying and not winning back. So no, they're not fair. There would be a positive expected profit for the, you could say, casino, lottery, etc., or an expected loss for the player. All right, that's why it's called gambling, because you're hoping in the short term you might get lucky, but in the long term, no. Okay, great. So there are some more problems that you can try out, and I will see you in the next video. Thanks.